Hi everyone, I am Francesco Lombardi, and with this presentation I'm going to introduce you to TurboSPORES, which, as the name suggests, is a computational improvement of the existing SPORES approach that we developed last year to generate out of energy system optimization models a wide range of spatially explicit, equally feasible alternatives for renewable capacity deployment. And the reason why SPORES need a computational upgrade is for the method to be applicable to models like the one you can see on the animation on the right hand side of this slide. That is, models covering the whole of Europe, but with spatial resolution high enough to reach the subnational scale that matters for real life decisions. Now, before going into the details, let's take a quick step back and clarify a little bit the context. We're talking about supporting the rapid and deep decarbonization of energy systems, and while it's clear that to achieve such a decarbonization we need to deploy a lot more new renewable capacity, exactly how much capacity or which technology we should deploy and where remain open questions. To shed light on such questions, we typically use energy system optimization models, which allow us to identify the system configuration that will make decarbonization possible at the lowest cost for society. Unfortunately, cost-optimality has little real-life meaning. As we can see in this example, representing the cost-optimal deployment of solar and wind capacity in each Italian subregion to fully decarbonize the Italian power system, cost-optimality would entail concentrating a very large share of all wind farms into a single region, which is the island of Sardinia, which would in turn likely lead to local opposition. So in other words, many factors other than cost are at stake in a real-life decision process about infrastructure deployment, and most of them cannot be parameterized into a mathematical problem at all. Not only cost itself in a model is affected by the uncertainty around all the assumptions about future technology costs, and as such, it is silly to fixate on what is the minimum cost configuration if we consider that some of the apparently more costly options might be just as cheap or even cheaper after such an uncertainty is realized in practice in the real world. So it's pretty clear that it would be much better if we could explore all the feasible different alternative system configurations, and we even have methods to do so, which are known since the 80s in the field of operations research under the name of modeling to generate alternatives, or MGA in short. The problem is that so far, applications of MGA to energy system models have focused on generating alternatives just in terms of technology mixes. What we instead additionally want to know is whether there are, for a given technology mix, spatially distinctive ways of locating capacity, say wind farms, at the subnational scale. So this is what the SPORES method is precisely conceived to do. And in this figure, we see one possible alternative way of locating solar and wind capacity that still allows us to decarbonize the Italian power system, but at the same time avoids unfair concentration of wind farms in any given region. And this is just one example of many options of this kind that you can find in the publication linked at the bottom of the slide. Now, let's have a look at the algorithmic workflow behind this. First, we identify the optimal solution by cost minimization, just as a starting point. Then, we need to assign weights or scores to each location technology combination proportional to their spatially explicit degree of technology deployment. For instance, let's imagine that the cost-optimal solution for a simple energy system with 3 regions is represented by the sketch at the bottom of the slide. In this case, we would assign a high weight to wind in region 1 because wind is deployed a lot in such a region, while we would assign a low weight to wind in region 2 where it's little deployed. If we assign weights in such a way, we can reformulate the problem with a new objective function, which now seeks to minimize the appearance of those location technology combinations which have been already explored in the previous iteration, which means that have been assigned a high weight. At the same time, of course, we impose that the cost cannot exceed by more than a certain amount the identified minimum possible costs, just like in conventional MGA. However, unlike for conventional MGA, SPORES are making explicit the search for both technologically and spatially distinctive solutions, which allows us to get the kind of subnational diversity that we are looking for. So this type of formulation can be repeated as many times as needed, each time updating the weights by the same logic, ending up with hundreds of feasible spatially distinctive alternatives. In addition to this, the SPORES workflow also foresees parallel runs in which a secondary objective is added to the search for spatially distinctive solutions. And such a secondary objective is the overall minimization or alternatively maximization of the capacity of a specific technology. This is needed as increasingly recognized by the literature to make sure that alternatives are originated along different search directions from several vertices of the decision space rather than just along the direction which arises from the cost-optimal vertex. And we will see in a moment a clear example of what this means. Again, we can end up with hundreds or potentially even more spores, considering that we can now also take advantage of the parallelization. Now, while the SPORES method has been successfully applied in this form to Italy, the application to the whole of Europe requires making the computation as efficient as possible, for instance, reducing the generation of redundant alternatives which are similar enough to each other and that could be therefore skipped altogether. To this end, we test here 4 alternative methods to assign weights to each location technology combination. The first is the integer weight assignment method, by which we assign an incremental score of +1 to a given location technology capacity variable whenever this has been non-zero in the previous iteration. The second method is the relative deployment method, which is what we use for the Italian study. In this case, the score is proportional to the amount of capacity of technology deployed with respect to the maximum potential for deployment of that technology in the given location. The third method is a random one, in which we just assign a random number between 0 and 1 as the weight without any particular rationale behind. Fourth and final, we have the evolving average method, here introduced for the first time. And this is as well the only method that explicitly keeps a memory of what has happened in previous iteration. In fact, it keeps track and continuously updates the average capacity deployed for each technology in a given region. And the closer to such an average is the capacity deployed by the subsequent iteration, the higher the assigned weight. We can now move forward to seeing how each of these methods performs. In this plot, we can see on the y-axis the total renewable capacity deployed by a given solution with respect to the maximum potential for renewable capacity deployment. On the x-axis, the same thing for transmission capacity, and with color coding, the same thing for storage capacity. The cost-optimal solution is identified by a red cross, and the spores arising from the first basic run of the workflow are those bubbles on the left. Focusing on just the first run of spores, which means excluding the parallel runs, is needed to clearly see the effect of the weight assignment method without the noise that is brought about by the more complex full workflow, as we will see in a moment. At first sight, the evolving average method seems to be clearly superior to the others in how quickly it spans a large area of the solution space, avoiding redundant solutions. If we now add the additional spores generated by parallel runs, however, we see that all methods start to become more similar to each other, which confirms how important it is to have these parallel runs to explore the solution space from multiple directions and capture the boundaries correctly. But in terms of redundancy, it does seem that there are differences. It seems that integer and relative deployment methods produce more redundant solutions, which means solutions that almost overlap in these plots due to having similar technology mixes. However, these almost overlapping solutions are precisely what the SPORES method seeks. That is, solutions with similar overall technology mix, but with spatially distinctive ways of locating capacity at the subnational scale. So, it is not so straightforward to decide what is redundant and what is not. The results highlight a clear trade-off in the computational efficiency of different weight assignment methods. The better a method is at finding technological diverse solution, such as the evolving average one, the worse it is at generating spatial diversity around the roughly fixed technology mix. And in fact, if we count, as we do in this bar chart here, how many spores for each method satisfy some of the criteria that we had identified in the Italian study as likely appealing to different real-life stakeholder groups, such as the low concentration of wind farms or the high utilization of newly built transmission lines, what we see is that integer and relative deployment methods substantially outperform the others. And this is precisely thanks to a higher presence of those apparently redundant solutions with similar technology mix but distinctive spatial configurations. So a good compromise could be combining the pros and the cons of different methods into a hybrid one. For instance, one that uses the evolving average method for the initial basic run of spores to explore quickly many relevant technology mixes, and the integer method to generate spatially distinctive alternatives from multiple search directions through parallel runs, in which the technological aspect is already handled explicitly through minimization or maximization of a specific technology. Such a workflow would look pretty much like this. The purple spores are here those generated by the evolving average method spanning a large portion of the technology mix decision space, whereas the blue spores are those with higher spatial diversity, generating around the technology explicit vertices identified here by black crosses. So we can hence summarize a few key takeaways from this computational experiment. First, there's a trade-off between diversity of technology mix and diversity of spatial configuration in exploring the solution space. The second, this also means that no alternative is really redundant per se. Even a brute force exploration of all technology mixes, which has been proposed by a recent preprint just a few weeks ago, would likely miss most of the real-life appealing spatially distinctive options around the found technology mixes. Third, if this is the case, if this is the situation, perhaps the ideal strategy would be to have an initial as exhaustive as possible exploration of the decision space, followed by iteration with stakeholders, which could then indicate themselves those technology mixes around which they would like to see more spatially distinctive options. Fourth and final, a hybrid workflow might be in fact more suited for such an initial exploration, and the evolving average method alone can still be an acceptable first guess option when computational resources are limited and it's not possible to rely on heavy parallelization. Coming back to the end goal anticipated at the beginning of our presentation, that is the generation of hundreds to thousands of spores for about 100 subnational locations in Europe, we can say that with a hybrid workflow and the heavy parallelization ensured by our high-performance computing facilities, we can easily achieve such goal in a matter of hours. Some preliminary examples have been in fact recently presented at the EGU General Assembly and are accessible via the link reported here in this slide. So this is pretty much it. I thank you for your attention, and please don't hesitate to ask any questions. Thanks a lot.